Good afternoon, everyone. Can I get a thumbs up from people on Zoom just to make sure that you all can hear me? Perfect. Thank you so much. My name is Barbara Martinez Neda. I'm the research data scientist here at the library. And today I'm going to be giving you an introduction to machine learning, particularly thinking about the entire machine learning pipeline so that when you walk out of this meeting, you can be a little bit more familiar with the terminology that encompasses ML or machine learning, so you can continue your learning. Let me go ahead and turn on the laser pointer, just because I'll be pointing at a few things throughout the meeting. And I would like to start off with a general definition of what machine learning is. So machine learning, or ML, you might see it sprinkled as ML throughout the presentation, or even when you look up stuff online, ML refers to machine learning. It's a subfield of artificial intelligence. And nowadays, I feel like most of us have heard the term AI or artificial intelligence being thrown around. And the way that it's being used to represent things like ChatGPT, Gemini, Claude, chatbots that essentially use artificial intelligence to think. But all of these chatbots that we all have been interacting with are actually just one branch within artificial intelligence known as generative AI or Gen AI. So Gen AI, chatbots are one branch of AI. ML is another branch that's kind of like besides the chatbots that we have been interacting with. And when we're thinking about machine learning, the main thing that we are doing with ML is that we are trying to solve difficult problems and generate predictions by identifying patterns in existing data. So this part is very important. In order for us to be able to train a machine learning model, we need access to a large amount of data to look for patterns that will allow us to make predictions in the future. So I'll very quickly go over 3 branches of machine learning. The one that we're going to be discussing the most today is known as supervised learning. Supervised learning makes use of a type of data known as labeled data. So when we are trying to make a prediction in the future, we need to have trained on a labeled data set. Labeled means that we know the inputs and the outputs. Inputs being past information, like in this example of a spam email detection, the input would be the email that we received, maybe some metadata about the email, like the time that we received it at, how long it is, and the output or the label being a label that tells us whether this email is spam or not spam. So for supervised learning, we need to have historical data that we already know the outcome for. So if we are training a machine learning model that helps us detect emails, we need to know for some number of past emails whether they were spam or not spam. For unsupervised and reinforcement, I'll very briefly introduce them since they won't be the main topic of today. But unsupervised learning essentially has no labels. In unsupervised learning, we're essentially looking for patterns in the data, and we don't really know what patterns we're looking for. So in supervised learning, we're looking for patterns between our emails and the flag that tells us whether the email is spam or not spam. In unsupervised learning, we don't know what that output is. So an example I have here is customer segmentation. A company might have a ton of data from people who have purchased from them over the last couple years, and they want to create customer profiles. So they use machine learning to create one group of people who often buy makeup, one group of people who often buy, yes?
It seems like your audio is not working. So,
oh no. Please, if the speaker.
This goes on and off.
On and off, okay. Let me know if the audio gets shaky again, and maybe I will connect my other computer to use the other microphone. But it seems like it's working okay now. Maybe I'll speak a little louder because the mic is somewhere up in the ceiling. But yeah, let me know. Thank you. Yeah, so in unsupervised learning, we don't really know what patterns we're looking for. We just tell the machine, hey, here's this data, cluster people who have similar shopping habits. And then each cluster is going to create one new profile. In reinforcement learning, we are essentially allowing the machine to learn through trial and error. So this is often seen in something like robotics, where the robot is programmed to learn how to walk on its own or how to do something on its own. It learns by making mistakes. So again, I wanted to give an overview of the three, but the main one we'll be focusing on today is supervised learning. And within supervised learning, we have two tasks you can set up. You can have classification, where you're essentially predicting a categorical variable. Categorical meaning, in the spam email example, we have one category of spam email, one category of non-spam email. We're predicting one of two categories. The other type is regression. And if you've done some statistics, you might be a little bit familiar with this. But in regression, you're essentially predicting a numerical value that's in a continuous range. So for instance, you might be training a model that helps you estimate the price of a house. You would have a lot of input information, and then the output is a continuous dollar amount from 0 to a million, or depending how big of a house you're looking for. And just double checking that the audio is still working okay. Perfect. Okay, so today we're going to be focusing on a classification example. In case I haven't made it a little obvious, we're going to be looking at a spam email detector with some input data, where we're going to be looking at how the machine learns to predict whether an email is spam or not spam. So let's first take a step back and just quick show of hands. Have any of you programmed in the past coding? Okay, perfect. So you might have some experience with some traditional programming approaches. And if you haven't, I have some examples here. So in traditional programming, you probably have seen that the logic is human defined. Whatever it is that you want your program to do, you need to tell your program exactly, hey, like you need to follow these steps. So one constraint is that when you start doing very complex tasks, we are very limited by the programmer's ability to anticipate every edge case. So I have this process here. In traditional programming, we likely have some input data. In the case of a spam email detector, we might have some emails and some metadata about those emails. And we have some rules that we set up to determine the output. Is this spam or not spam? On the other hand, with machine learning, the logic is machine derived. So we essentially have access to a large data set. We give it to the machine to identify patterns in the data. And then this allows us to potentially find more complex patterns to make predictions. So here the process would look like having some input data, some emails and metadata, some outcomes. So we already know whether these emails were spam or not spam. And when we give it to the computer's task is to look for rules or relationships between these inputs and these outcomes, so that we can then make predictions on new emails that might come in at a later date. So primary advantage is that it solves tasks where rules might be too complex for us to think of edge cases. One downside that I don't have on the screen, but I mentioned a little bit earlier, is that you do need access to an existing data set. If you don't have data, you can't train a machine learning model. So let's go ahead and look at some examples of how your programming might look like with this. So in traditional programming, you might have written a little script that says, if my sender is unknown and the email contains the word urgent and bank account, we're going to classify this email as spam. Otherwise, if these conditions are not met, then my email is not spam. But then we're going to look at a couple examples. So let's imagine this email that we have on the screen came in from an unknown sender. Urgent, your package cannot be delivered. Click here to log in and update your bank account information. So let's look at the conditions that the programmer set up here. And can someone maybe take a guess as to whether our little traditional programming spam detector would detect this as spam or not spam? Spam? Okay, we hear a spam, and that is correct because we see here, like I mentioned, the sender is unknown. The email contains the word urgent and bank account. So the conditions are met. We successfully fall into the spam bucket. But let's look at this other email, which I'm sure many of us have seen. Hello, thank you for your $9.99 payment for your new iPhone 17. If you did not authorize this purchase, please click here. So not from our own past experience, but based on these conditions, would our traditional programming email detector classify this as spam or not spam? Right. So it would actually be, oh, it's not spam. Why? Because we don't see the word urgent and bank account. And yeah, I also see in the chat, not spam. So our email detector here would tell us, we're good, let's put this in the inbox. Now, when we use machine learning, you're gonna see this pipeline, and this is actually what we're gonna be talking about today. So don't worry about grasping all of it just now. We'll walk through it step by step. But essentially in machine learning, we have our email metadata. We have the flag that tells us if historically these emails were spam or not spam. The machine looks for patterns between these two. It produces a trained model that can then solve more complex questions. So our goal with this is to then get those two emails, and hopefully we gave it enough data to learn complex enough patterns to find out that both of these emails are actually spam. And then that way it doesn't go into your inbox. So now that we've talked big picture, kind of how machine learning, the definition of machine learning and how it differs from traditional programming, these are the steps we're going to go through today. We're going to start by talking about data collection, analyzing your data set, a step called splitting your data, pre-processing your data to get it ready for a machine learning model. Once we get through all these data-related steps, we can talk about training our model. And lastly, some steps for you to evaluate the model as well. So with that said, let's go ahead and get started talking about data collection. So when you're doing a research project, or maybe you're working on a class assignment, you might have produced a data set that you want to work with, or your professor might have given you a data set that you want to start working with. But if you are looking for places to kind of like get started with learning about machine learning, or you want to see how can I incorporate an existing data set into a new research project, these two data sets are very good places to start. The first one being the Kaggle datasets website, and the second one being the UCI machine learning repository. So I'll kind of start with like the right one with the UCI machine learning repository. This place essentially has a bunch of data sets that researchers and the community have uploaded for other people to just download and start training models. We can see it's kind of small, but we can see that it tells us, oh, this data set, this iris data set is good for classification. It has 150 records. This other one is good for regression. It has 3 million different records. So this is a good place to look for data. And then in Kaggle, you can not only find data, but you could also enter, sometimes they have like little online competitions. And even if you don't want to compete, a good place with it is that, a good thing with it is that people upload their code. So you might have programmed your own, machine learning pipeline, and you want to compare it to other people's, or you want to see, did someone, let me go do that. Yeah. Or did someone do something differently? You can look at the Kaggle website to look at other approaches to see what other things you could incorporate into your own code. So with this step, you would essentially go to the website. If you're kind of looking for a new project, go to the website, download a data set that interests you, and you could move on to the second step in machine learning, which is analyzing your data. So when it comes to data analysis essentially allows us to explore our data, find patterns, draw conclusions, and you might be asking yourself, well, isn't machine learning going to do all the pattern finding for me? Isn't that just going to work on its own? It is going to find some patterns, but before you even start training a model, it's very important that you familiarize yourself with your data set. You essentially need to become an expert in the data that you're working with so you can manage how the computer is working. Because if you don't have a good grasp of the data itself, the model might be behaving in a way that you can't really explain. And then when you go look at the reasons why, you'll kind of have to backtrack and see, well, what's up with my data and what is essentially causing this? Where if you take the time to analyze the data set, find any anomalies, anything that you have to fix, you could do that before we even start talking about machine learning. So I want to mention some data visualization, what's it called? Approaches you could start incorporating if you are not really sure where to start with visualizing your data. So going back to our email detection, let's imagine we want to count how many emails in our data set are spam, how many emails are not spam. We could use frequency tables, bar charts, or pie charts to represent our categorical data. But if we want to look at the distribution of a variable, like if we have a column that tells us how many words are in an email, we could look at that distribution using something like histograms, box plots, and density plots. And then lastly, if you want to be looking at relationships between variables, you could use scatter plots, line graphs, and heat maps, where one variable could be the x-axis, another variable could be the y-axis, and you can maybe start getting a sense of any relationships between the variables within your data set. So I will be making these slides available after the talk. So if you registered on Eventbrite, you will be getting these slides, so you have access to some of these informations. I kind of put that here so you could refer to it back later and start some of those visualizations. So at this point, we've collected our data set, whether it be from your assignment, your research, or online. You've analyzed it, so you have a pretty solid understanding of what it is that you're working with. Now we're going to move into the first machine learning focused step in our pipeline. So we're going to be doing a data split, where we're going to split our data into training and testing subsets of our data. So this is also known as data partitioning. So you might see this mentioned that way online. And essentially, with data partitioning, we are ensuring that our model is going to be able to find patterns that can generalize outside of just our training data. So we start with an original data set. In this case, it has like 10 rows, and the majority becomes the training data, the minority becomes the testing data. Our training data, as the name suggests, is used to train our model. Training our model means allowing the computer to find patterns between the input data, email information, and our output data, spam or not spam flag. The testing data, on the other hand, is going to remain unseen while we're looking for patterns, and it's essentially going to serve as a benchmark for us when we are looking to evaluate our model. So one way I like to think of this is, let's say we don't do a data split. It would be very similar to a professor providing the same questions on an exam as they did on their final exam. So if the same exact questions that the students saw on the homework are the ones on the final exam, like, do we know if the students actually learned, or did they just memorize whatever examples they were given? Very similarly, if we don't split, we won't know if our model actually learned to generalize and make predictions in the future, or if it just memorized patterns and it only really knows how to match like these inputs to these outputs, and then we wouldn't be able to use it anywhere outside of this use case. So by splitting the data, we solve this problem because this serves as an unseen set of questions for our model to make predictions on. So now we've talked about data collection, data analysis, splitting. Now let's talk a little bit about pre-processing. So data pre-processing, also known as data cleaning, is essentially the process of detecting, correcting, fixing, removing any records that might be inaccurate or incomplete. The main goals you have to keep in mind: make sure your data set is accurate. So if you have a survey and someone entered information with a typo, making sure that that's fixed, making sure it's consistent. So if you're asking someone in a survey for their favorite color and someone says green and someone says green exclamation mark and someone says GRN, like making sure that there's consistency between responses to make sure they all map to the same single response of green. Making sure it's complete, so no empty values, no outliers or extreme values. And lastly, making sure it's machine learning compatible. So for a lot of machine learning models, your data needs to be in numbers. And if you have text data, you would have to find ways to turn it into numbers. So for today, we won't go super deep into the data cleaning process, But I did give a workshop earlier this quarter on data cleaning for machine learning, specifically using Python. So if you're interested in watching that, I've linked the video down here, and we essentially go through all the steps that you would be able to take using existing libraries, the Pandas library, to get your data set ready for a machine learning model. But essentially, what we would see is that we typically start with a raw data set that might be a little bit dirty, or it has some things that are wrong with it. So just looking at it, can anyone maybe tell me, based on the checklist that we have here, maybe some things that might be wrong with this data set? And then AI kind of pre-circled some of them for us. Any things that might be wrong with this data set? Any thoughts?
Somebody in the chat.
Let's see. Yeah, so we have text. That's a good one. So we need to make sure that it's no longer text at the end, so it's machine learning compatible. Another one is that we have some empty values. So we need to make sure we don't have empty values before we go to machine learning. Yeah, missing values, we'll drop NA, blanks, perfect. Another one, like if we see here, when we see the sender status, we see, we also see outliers, yes. So we have a sender status of unknown, friend, and known. Friend and known could probably be the same thing. So there's some inconsistency there. For us, all we really care about is this person in our like saved contacts, or are they not? So we would need to maybe handle that before giving it off to the machine. And then I see here, we have some outliers. So if we see in this character count column, most are in the hundreds of characters. And then we have one that's like really big. So after following some of the steps that we could that you could follow in the linked video, we would essentially see that unknown is mapped to 0, friend and known are mapped to 1, unknown again to 0. The empty values are filled out, and then one of the steps is also scaling them. So if you see these numbers are from 0 to 5, here we have it on a scale from 0 to 1. So they're just, all the columns are on the same scale from 0 to 1 to make sure that our model doesn't think that one column is very important just because the number is very large. So yeah, if you're interested in kind of seeing how we can get from this table 1 to this table 2, this video is going to outline a lot of those steps for you. So let's move on to the machine learning training phase. So now that our data is split and pre-processed, we can begin talking about training our machine learning model. So I would like to start by kind of going through the model training pipeline. We start with our original data, which for our email example is made up of email metadata, and then a flag that tells us whether each of these emails or each row is spam or not spam. We split our data into the training set and the testing set. We kind of leave the testing set kind of hanging out, doing nothing for a little while. But we grab our training data and we use it to train the model. When you hear training a model, it means that we allow the computer to use an algorithm to find patterns between these inputs and these outputs. This then produces a trained machine learning model that could be used to make predictions in the future. So as we see here, we can grab our testing data and generate some new predictions with our trained model. So we feed the unseen test data through the trained machine learning model to produce some new predictions. So if you see here, all we really fed from our testing data was the email metadata. We did not pass the flags because these flags are only going to serve as an answer key after we make these predictions. So we grab the email information and metadata, we pass it through the trained model, and we make some predictions that we're then going to compare to this further down the line. So for this, I wanted to go through one algorithm just to give you a sense of what happens inside of these two steps of the training the model and the trained model stage. So the decision tree algorithm essentially looks at the data that we give it. It tries to find patterns between the inputs and the outputs, and it tries to represent the relationships that it finds using yes or no questions. So we have our training data that goes into the train the model stage to produce a decision tree model. Let's look a little bit at what that looks like. So let's say that this is the data that we have available for our emails. So we know whether the sender is known or unknown. We know whether the email contains the word urgent or winner. We know how many links are present in those emails. And we also know whether those emails were spam or not spam. And I know for machine learning, there shouldn't really be text a lot of the time, but this is more just for like our understanding as we go through the example. This is the data that we have available about our emails. So what does the machine learning model do? It looks for any pattern here that could link it to the spam column by asking a yes or no question. So I will highlight essentially one thing the machine could find. It could find, oh, you know what? Every time the sender is unknown, that email is spam. I'm going to represent that relationship by asking the question, is the sender unknown? If the sender is unknown, then we're going to know that that's a spam email. So that kind of solves one case, but then that leaves us with still some data where we need to look for some relationships. So it keeps looking to see what other relationships are present between the inputs and the outputs. And then it might look at the next column of urgent and winner, and it might notice, hey, every time, like ignoring the ones that are bolded and italicized, because those have already been handled by this question. Looking at the remaining records, every time we see the word urgent or winner from a known sender, those emails are also spam. Okay, maybe we'll ask, does the subject contain this word? And if it does, we also know those are spam. Then that handles some more cases. Then it might say, well, another relationship I found is that if there's a ton of links in the email, then those are spam as well. So then it might ask the question, well, does the email have 3 or more links? And if it does, then we're going to go ahead and classify that as spam. And that leaves us with 3 remaining ones. And those happen to all be not spam. So then the model could just say, you know what? If this condition is no, and this condition is no, and this condition is no, then we're going to classify it as not spam. And the main thing to keep in mind here is that all we really had to do was find a data set, prepare it for the machine, and then the machine did all the work of finding these relationships. We don't determine those relationships. The machine looks for relationships between the gray email metadata and the red-green spam flag to come up with a model that you could hopefully take out to the real world and give it new data to see how it performs there. So two terms I want to introduce very briefly, just so you are familiar with them as you continue your learning, are underfitting and overfitting. So underfitting essentially happens when your algorithm, in this case a decision tree, is too simple. It essentially hasn't asked enough questions or it hasn't found enough patterns to generalize well. So this would be a tree that, or like an algorithm that's underfitting. It only asked one question. Is the sender unknown? If so, it's spam. If not unknown, not spam. This probably wouldn't generalize very well for us, like implementing it into our own inbox. And then the inverse would be overfitting, where your algorithm, in this case a decision tree, finds very specific relationships that only really apply to the training data that it like looked for patterns in. So that would be something like, well, was the email sent at 4:03 p.m.? Like it starts finding very specific patterns that only make sense on the data set, like the training data set. But once you give it the test data, this is completely irrelevant, and it might actually make your model predict incorrectly. So our goal is to essentially find the middle point between underfitting and overfitting to build a generalizable model that asks just enough questions to be accurate, not only on the data that it trained on, but also data that it sees coming forward. So the way that you would do this is by changing some settings once you get to the code. And I do have a coding example at the end, so I will point out the area where you could start playing around a little bit with finding the middle point between underfitting and overfitting. But I did want to share these two terms with you. And at this point, we've gone through the entire training, like data preparation and training, model training pipeline. The last step is evaluating our model. So at this point, we've built a classifier that can make predictions on new data, and we're hoping that it performs really well. But we're not really going to know how well or how poorly it performs until we evaluate its performance on unseen data. So we had our little pipeline from earlier, where we essentially started with a data set, we split it, trained the model to have a model to use for predictions later on. And after we generated these predictions, we essentially fed a test data set through the decision tree model to make new predictions. And now we evaluate the model performance. How do we do this? We compare the predictions from the model to, I like to think of it as an answer key, the true testing values. Because if we remember here, we grab the email metadata, we fed it through a decision tree algorithm to tell us, hey, we actually don't know. We don't know whether these emails are spam or not. Can you tell me what you think based on the model that you trained? It makes a decision. In this case, with green, it tells us, oh, both of these are not spam. But if we look at the answer key, we actually see that some are incorrect and some are correct. So this evaluation step is what's going to allow us to see how well our model is performing. I want to introduce you all to some performance metrics to consider when you're evaluating a model. So to make sure that a model generalizes well to new data, we need to evaluate its performance on unseen, in this case, test data. And a very useful little table is this confusion matrix here. So when we make predictions on a data set, we're essentially partitioning how many of these predictions were initially spam emails that were successfully predicted as spam. These are true positives because they were actually spam and they were predicted as spam. So it's a true positive. The next segment we have is emails that were initially spam, but they were predicted as not spam. So this is a false negative because it incorrectly predicted that this email should not be put into the spam inbox. The next section we have is a false positive, where we have not spam emails that should have actually been predicted. Sorry, the opposite. We have not spam emails that were predicted as spam. They should have been predicted not spam, but they were incorrectly predicted as spam. And lastly, we have true negatives. These are emails that were not spam, and the model successfully identified them as not spam. And might be a little much to grasp at the beginning, but I do just want you to familiarize yourself with the terminology as you go out there and continue learning about machine learning. What's a confusion matrix? Oh, I already know that terminology. Or maybe you're starting to think about evaluating your model. You don't really know where to get started. Confusion matrices are a good place to start, as well as some of the metrics I'll have on the right over here. The most common one being accuracy, and I think this is also maybe the more intuitive one. Accuracy just tells us the proportion of the total predictions that were correct. If we had 100 emails and 80 of them were correct, we had an 80% accuracy. But if we want to start breaking down into more precise, I would say, metrics, we could also look at precision, which is a ratio between true positives and all the positive predictions. In our spam email detection example, we would essentially be asking ourselves the question, of all the items that we identified as spam, how many were actually spam emails? So we want to see, well, I guess like I almost feel like I'm repeating myself. So of all the items that the model predicted, did it make any mistakes in it and incorrectly predict a not spam email as spam? So a little bit of the inverse of that is recall. So a recall is a ratio between true positives and all real positives. So here we ask ourselves, of all the actual spam emails that exist in our data set, how many did the model successfully find? So this would be very important if like you're training a model and you want to make sure you don't miss a single spam email. You want to make sure every single spam email is going into the spam inbox. So that you would train a model that is maybe maximizing for recall in that case. But with that said, we've essentially covered all the steps present in supervised machine learning, starting from data collection, moving on to analysis, pre-processing, splitting, training, and finishing with evaluating. I do have a short, very simple coding example. And I don't mean simple like if you haven't programmed before, the syntax might be confusing, but I mean simple like the data set that I'm giving it is not like real world thousands of records. It's only like 10 or 15 records, but I just want to give you all the gist of some of the libraries that you could use. So let me go ahead and switch over to a Jupyter notebook. I just quickly want to go through the steps with you all. So when we go from the theory into implementing into a Jupyter notebook or a Python notebook, the first thing we need to do is import dependencies. This essentially means we can import libraries. So if you haven't programmed before, libraries are essentially toolkits that people have built for you to make use of them. So when you're doing machine learning, all you really need to worry about is maybe understanding the syntax of some of these libraries, but also understanding the theory, like how the model works. You don't need to worry about how can I write my own algorithm that implements a decision tree. Someone already did all the code for us. All you need to do is import the relevant library. In our case, it's named the sklearn library. This library is, I would say, one of the core machine learning libraries. And then this would allow you to load the relevant algorithms that you want to interact with. So we hit the play button to successfully import our libraries. And here's the data set I created for today. So this is just a sample data set and has some metadata columns about our email. So when we load this, the data set we're going to be using essentially tells us whether the email comes from an unknown sender, how many links are present in our email, does the email have an attachment or not, and finally, the label. And you might see only numbers. Like I mentioned with machine learning, oftentimes you need to have a numerical representation for your data. Up here, I've included a key. So an unknown sender, 1 represents yes, it's unknown, 0 is not unknown. Link count, that's just a number. But similarly for has attachment, 1 represents yes, 0 represents no. And lastly, the label 1 represents spam, 0 represents not spam. So we have our little sample data set. And as we saw on the slides, we need to split our data into a training data set and a testing data set. sklearn has a built-in function called train test split, where you tell it, hey, I want the columns unknown sender, link count, and has attachment to be X. And in code, oftentimes when you hear X, that's the input. That's all the email information that we know. And then our Y or our output to be just label. And we want 20% to go into the test set, 80% to go into our training set. We run this, and what we're going to see is that this line of code here, just one command, essentially split our initial data set into 2. So originally we had 20 emails with 4 columns. We ended up with 1 training set that had 16 emails with 3 columns, and then a Y train, which is the labels, which has 16 spam inbox labels. And then we have the testing set with only 4 emails, or 20% of the data, and then 4 spam, not spam labels for it. So at this point, we've imported our data set. In this case, we created it. We split it into train and test set. Now we're ready to train our decision tree model. Like I mentioned at the beginning, when you are doing machine learning in Python, a lot of libraries already have implemented the code for you, where all you have to do is write 1 line of code and familiarize yourself with the documentation, which I'll link to you later in the slides. So here, all we have to do is declare in 1 line, we're going to be using a model, or inside, like for this model, we're going to use the decision tree classifier. And earlier I mentioned the part where we want to find the balance between underfitting and overfitting. Like we want our algorithm to be not too simple, not too complex. This would be the area where you would be messing around with the settings. So in this case, the only setting we really have is how deep or how many questions deep our model can go. We're going to set it to 3, but if you wanted, you could make it 10, you could make it 1, and then it might get very simple. But when you start playing around with other classifiers within this library, this area where you declare your model is where you're going to be essentially tweaking some of the hyperparameters to be able to find that middle ground between simple and complex. So the second line we have here, and let me actually split it. So when we run this first cell, all we're doing is we're creating this model that we're going to be able to use to make predictions. And this fit command is essentially telling us, using our decision tree model that we declared up here, I want to fit. Fit means train. It means find the patterns between the inputs and the outputs. X train being the inputs, Y train being the outputs. So X train is the email metadata, and then Y train is whether it's spam or not spam. So when we run this little blue box tells us we've successfully found patterns using the settings that you gave me. And at this point, we're ready to make some predictions. Again, we're using our decision tree model, which we just named model. And we make a prediction by using the predict command. So model.predict followed by our test data set is going to give us some predictions. And the thing to notice here, when we were fitting, when we were looking for patterns, we looked for patterns between X train and Y train. Over here, we only give it X test. The reason we do that is that we're pretending it's unseen data. Like we're telling it, hey, here's the information we know about the emails. We don't know if they're spam or not spam. We want you to make that prediction and store it into YPred or YPredict. So we run this. And at this point, we can start looking at some performance metrics. And just to show you what YPred looks like. So first, let me show you X test. So X test is just the inputs, unknown sender, link count, has attachment. We don't know if it's spam or not spam. We told the decision tree, hey, make some predictions. Let's see what it gave us. And we see that for the first element, it predicted 1. For the second one, it predicted 1. The third one, it predicted 0. And the last one, it predicted 1 as well. So those are our predictions. Now we can move on to the last step where we evaluate our model. And while on the slides, we had all these formulas. I mean, you could calculate it manually if you'd like. But again, the libraries already have pre-built performance metric calculators where you just tell it, hey, I want to see the accuracy score by comparing the Y test or the spam, not spam from the test data set versus the predictions of the model. I also want to look at precision and recall. So we run this. And our model, again, it was a very small data set. Oftentimes when you're training a machine learning model, your performance metrics are not going to be 100%. This is just best case scenario where your model just generalizes very well. But yeah, typically you're going to be able to look at accuracy, precision, and recall to give you a sense of, okay, well, we train on some unseen data. We trained on some training data. We evaluated on some unseen data. What are the performance metrics for that? In here, I've also included the code for how to plot a confusion matrix. So again, you don't have to worry about writing all the code. Someone developed a little function for you to just say, hey, write a little confusion matrix using my Y test and Y predict, and it's going to show you how many true positives, true negatives you have. But with that said, I very briefly want to share some additional resources. So if you haven't programmed before, I just want to share that there's something typically called documentation that goes along with all the coding libraries. So like I showed you all right now, with one line of code, you train a model. With one line of code, you evaluate the model. Where do you learn all those terminologies? You go to the documentation of the library. So if we go here, we can see the scikit-learn library has a ton of information. Like if you want to do classification, we're gonna, well, there's a lot, but I just want to show, we have decision trees for classification. It tells you some sample code to get started. It's a little small. But essentially you would be able to see all the models you could use for supervised learning. I think they also have like unsupervised and whatnot. You want to do a linear model, support vector machines. These are all different ways for the model to learn the relationships between input data and output data that it's going to predict. So always look for the documentation of libraries. I also linked here some pre-processing steps that you could take also using the sklearn library. And other online resources you could use. W3 Schools and Geeks for Geeks have pretty solid starting guides, I would say. And then over here, I've also linked Kaggle, which I mentioned had some competition. So you could see, like, if a very popular one is this Titanic prediction, where you're essentially, let me see if the data set's available. Yeah. So you have a lot of information like the sex, the class of the ticket that they bought, the age of the passenger, and then people use all this information to try to predict whether a passenger survived or didn't. So that's a common competition on Kaggle. We have house prices, like I mentioned, right at the beginning of the session. So you could come here to learn a little bit more. And then if you're looking for kind of like in-depth, how do the algorithms work and what are all the algorithms out there? I've heard really good things about this Coursera course. And I'm pretty sure you don't have to, like, you can just enroll for, you don't get the certification at the end if you don't pay, but they have pretty solid courses that touch on some of the same libraries that we covered today. So scikit-learn, supervised models. So essentially finding patterns between inputs and outputs, binary classification. And this essentially covers like a bit of the math behind like finding all the patterns. With that said, I'm the research data scientist. If you have any questions, not only about machine learning, but working with your data set, data management plans, incorporating ML into your workflows, into your research projects, please feel free to reach out over email, consultation. There's also more, well, this is the last workshop for me this quarter, but we have workshops every quarter, so you could always drop in to learn about a different data topic. And we have, I believe we have one workshop left of our AI series this quarter, which is this Intro to Deep Learning with PyTorch next week. But I would say we're probably going to have something similar to this in upcoming quarters, just to tackle different aspects of machine learning. And lastly, here at the library, we have the Star Lab that has 4 workstations that you could use for higher performance computing tasks. Like if you want to get started with deep learning, machine learning, setting up a local language model, you can drop in and use the machines. If you are maybe interested in what you can do with them, you could always reach out to me and we can talk a little bit about what you can do there. But thank you all for dropping in today in person and online. If you have any questions, please feel free to ask them. We still have some time, so happy to help. And yes, I will be sharing the slides. Maybe within the next week for sure. I will update the slides, and let me double check. I'm pretty sure the session is being recorded. Yes, so I'm currently recording the session, so I'm also going to be uploading that to YouTube. That might take a little bit longer because we got to make sure transcripts are good to go and all of that, but at least the slides will be going out within a week. Yes. Yeah. Yeah, thank you all for coming. Any questions?
Is the 80-20 differential like a standard, or do you play around with differential?
Yeah, good question. So 80-20, I think, is kind of like the default people go to, because generally you want to have as much data as possible for your model to find as many patterns as it can, but you still also don't want to give it like two examples to test on. So 80-20 is the default, but if you have like thousands of records or like tens of thousands, even consider doing something like 90-10, where you train on 90% of the data and then you test on 10. But not as often. I've seen the opposite, where they do like 60 or 70% train and then 40 validation. But yeah, there's other techniques to, if you're interested, we could talk more about it after, like where you essentially create like 5 copies of your data set, and then you do like 80% training, 20% testing. And then for this one, you do like 80%, like the bottom 80%, and then the top 20%. And then for this one, you do the middle 80% and like the outer 20%. Like it's a little confusing, but people sometimes do that to like kind of, if they're having the challenge of not having enough data. So they kind of like augment a bit of the data that they have that way. It's called cross-validation, if you're interested in that a little bit. I have a question about using R. So personally, I know that you can do a lot of machine learning things with R. I haven't implemented them myself, but I would be more than happy to check in with some of my colleagues and share some information after the meeting as well. And maybe Brendan, if I could ask you, have you used machine learning in R?
I haven't.
But there are libraries, right?
Yeah.
Okay. So there is some compatibility with R. I'll just do a little bit of okay. Perfect. So I'll definitely be looking into those for researchers that are leaning more into the R side. But yeah, if we don't have any more questions, I think we're good. Oh, we have one more question.
I'm sorry. I was just wondering, for the machine learning, do you have to make a machine by yourself and then train it, or can it be like on an existing machine as well?
So machine learning, and I felt very much the same way when I first heard the terminology. Let me see. This line, these 2 lines are like the training stages. So you don't have to do anything because someone already created a library that looks for patterns between inputs and outputs. So this like fit essentially generate, like it's just a file that stores it's not in plain English, it's just like put all the computations between inputs and outputs. But you don't need to create your own machine. Someone already developed a library. I mean, if you're interested, you could definitely start it from scratch and write all the code for it. But essentially, this in the back end is just a bunch of instructions and calculations to represent those patterns from inputs and outputs.
can we like make it do anything we want? It's like a base for everything, like every scenario, is that?
Yeah, so the question was, can we train it to do anything specific that we want? So in this specific case, like we wanted to train a model that predicts whether an email is spam or not spam. So we gave it data that had email information and then like outputs, like are they spam or are they not spam? If you want to train a model that like a common example I see online is should I wear a sweater outside? And then they need to have a large enough data set that takes in temperature, sunlight, is it cloudy, is it rainy? And then you have all those inputs and then the outputs of should I wear a sweater, yes or no? So you could train it to do anything you want as long as you have data for it to learn from. Of course. Okay, well, thank you all again. I will go ahead and hang out here for a few more minutes, but I think we're good to wrap up the, Thank you.